So we've looked at what the effects of capacitive reactance has on a circuit. And at this point, we're all only really talking about a purely capacitive circuit with a sinusoidal power source applied. So thus far, we've determined a proportional relationship between X sub C, the capacitive reactance, and 1 over the frequency times the capacitance. So now we need a mathematical relationship. We need a formula that tells us what the capacitive reactance X sub C is equal to so that can be calculated. So since we started with this X sub C and 1 over FC relationship, the relationship that we need for capacitive reactance is 1 over 2 pi times the frequency times the capacitance. The capacitive reactance, X sub C, is in ohms when the frequency is in hertz and C is in farads. So you'll notice in the denominator we've added this 2 pi relationship. Well, this adds in our cyclic sinusoidal relationship that we need in order to calculate the capacitive reactance. So notice that the 2 pi appears in the denominator as a constant of proportionality, 360 degrees. This term is derived from the relationship of a sine wave to rotational motion. So let's see, how do we use this relationship? So if we look at this a little example, a sinusoidal voltage is applied to a capacitor shown in the figure. The frequency of the sine wave is 1 kilohertz, 1 kHz. Determine the capacitive reactance. So we know the frequency from the diagram. We know the capacitance, 0.0047 or tens, hundreds, thousandths, 47 thousandths of a microfarad is our capacitance. So we can start dropping those into the relationship. X sub C is equal to 1 over 2 pi FC. So when we do that, 1 times 10 to the third, that's our kilohertz. 0.0047 times 10 to the minus 6, there's our microfarad, our value. And if you run this through the calculator, again in your calculator, make sure you always use the pi key. Don't type in 3.14 blah blah blah. Enter the pi key, multiply it times 2, and then do the rest of your relationships. Multiply these together and then do an invert, and you'll get 33.9 kilohertz, or kilo ohms in this case. We're calculating the ohmic value of the capacitive reactance. So as we've seen from the previous representations, the previous slides, that the current leads the voltage by 90 degrees in a purely capacitive AC circuit. If the applied voltage is assigned as a reference phase angle of 0, it can be also expressed in polar form. This is the polar form of that relationship. V sub S, the source, at some angle 0. The resulting current then can be expressed in polar form, the same thing. Current at an angle, in this case 90 degrees, because we know that the current leads by 90 degrees, or in rectangular form using the J operator, Ji. So let's look at a couple of examples we've seen. You know from your DC classes how to handle capacitors in series and how to handle capacitors in parallel circuits. So first let's look at the series capacitor. Reactance for a series capacitor. When capacitors are in series in an AC circuit, the total capacitance is smaller than the smallest individual capacitance. I hope you recall that from ET131. Because the total capacitance is smaller, the total capacitive reactance, or opposition to current, must be larger than any individual capacitive reactance. With series capacitors, the total capacitive reactance, X sub C total, is the sum of the individual reactances. And so you can see we just summed all of our values here, our ohmic values. Compare this formula to what you learned in ET131 for finding the total resistance of series resistors. In both cases, you simply added the individual oppositions. For parallel capacitors, dealing with reactance, in AC circuits with parallel capacitors, the total capacitance is the sum of the capacitances. Recall that the capacitive reactance is inversely proportional to the capacitance. So you can see we have 1 over XC added to 1, 2, 3 off to the nth capacitor. We do that, and then we do our inversion. Because the total parallel capacitance is larger than any individual capacitances, the total capacitive reactance must be smaller than the reactance of any individual capacitor. With parallel capacitors, then, that is the basis, the formula, the general formula. If we compare this formula to, again, the formula we learned in ET131 for parallel resistors, as in this case of parallel resistors, the total opposition, resistance or reactance, is the reciprocal of the sum of the reciprocals of the individual oppositions. That's exactly what we see in the general relationship. So for two capacitors in parallel, then we can say that it can be reduced to the product over the sum form. Again, this should be something you're familiar with from ET131, the product over the sum. So this is useful because for most practical circuits, more than two capacitors in parallel is not common. So let's take a look at an example here of series and parallel circuits. So in A, we've got a series circuit. In B, we've got a parallel circuit of capacitors. So what's the total capacitive reactance in each? So the reactances of the individual capacitors are the same in both circuits. You'll notice that they have the same values given. So when we calculate step 1, find the individual resistance values or capacitive reactances for each, we run it through the formula 1 over 2 pi FC, and we end up with 3.18 k ohms and 468 ohms for our capacitors. So for the series circuit, we take and just add our values together. X sub C1, X sub C2, sum together gives us 3.65 kilo ohms or k ohms of resistance. Alternatively, though, you can obtain the total series reactance by first finding the total capacitance using the capacitance formulas, okay? So they show you here, you can do the same thing using a product over the sum of the capacitances. So if you C1 times C2 added to the sum of the two, you get 87,000 microfarads, and then run it through the reactance formula, and you end up with, you can see, the same value. In the parallel circuit, though, for capacitors, if we determine the total reactance from the product over the sum rule, so we skip right to the product over the sum because that's the easiest with two capacitors, you can see that we take the product of those two values that we calculated previously, take the sum of those two values, and we get a total of 408 ohms for our value. Notice, smaller than the smallest. Okay, so where we had 3K, here we had 468. That's the smallest. This becomes smaller than the smallest. We can also use our Ohm's law relationship for reactance, calculating our reactance values. The reactance of a capacitor is analogous to the resistance of a resistor, okay, because it's just a resistance value. So we can apply Ohm's law since R and X sub C are forms of opposition to current. Ohm's law applies to capacitive circuits as well in resistive circuits. So we can state for current, which is E over R, okay, V sub S over X sub C, we can come up with our values. So again, a simple circuit here where we've got, so looking at the circuit then, we've got one capacitor, we've got our voltage source, 10 kHz source, 5 volts, and 56,000 microfarads. So again, the first thing we're going to do is determine the capacitive reactance. So we take our values, 2 pi times 10 times 10 to the third hertz, and our capacitance values gives us X sub C of 2.84 k ohms. Now we apply Ohm's law. We just use this relationship for in this case, we're going to calculate the RMS current. VRMS is 5 volts because that's what was given in the circuit example, divided by X sub C. We get 1.76 milliamps of current. Again, this is an RMS value. You'll recall, again, from your ET131 course, using voltage dividers where we had resistive circuits. Well, we can do the same thing with capacitance voltage dividers, where we determine what a voltage drop is, or where we can do a pickup voltage on a small circuit. So in AC circuits, capacitors can be used in applications that require a voltage divider. An example here, oscillator circuits will use this method to tap off a fraction of an output. And you'll remember from your ET131 how you did that in your lab and measured where you could do pickoff points for a voltage divider. So the relationship here says V sub X, what we're solving for, is the ratio of the total capacitance to the capacitor X and the source. The resistive voltage divider then is expressed in terms as a resistance ratio. So where we use capacitance here, we can use capacitive reactance down here. The equation for the voltage across a capacitor and capacitive voltage divider then is written as the ratio of X sub C X to X sub C total, and multiply it times the source. So let's look at an example. What is the voltage across C2? Okay, so we've got a voltage divider here where we've got pickoff points here, and here for the total with C2 and with C1. The reactance of the individual capacitors and the total reactance is determined, okay, from a previous example. If you want to go back and look at the previous example, otherwise run this to 1 over 2 pi f times the capacitance, and we get our values of 468, 3.65 k ohms. Okay, that was our previous example. So when we run this through the voltage divider formula, times 10 volts, because that's the source voltage, we get 1.28 volts. Notice that the voltage across the larger capacitor is the smaller fraction of the total. You can obtain the same result from equation 1212 previously. Okay, so we're using the capacitor values instead of the reactive values here to calculate the same value. Power in a capacitor. Power in a capacitor is a little tricky because we've got more than one type of power that we glean from a capacitor. You can see here that we've got voltage and current, which are our normal terms for calculating power. In this case, V times I, and we've got a power curve then generated from the two terms here, voltage and current. So as discussed in an earlier chapter, a charged capacitor stores energy in an electric field within the dielectric, unlike a resistor that totally dissipates the energy, usually as heat. An ideal capacitor does not dissipate energy. It only stores it temporarily. And if you'll recall, it swaps the polarity back and forth between the plates. When an AC voltage is applied to a capacitor, energy is stored by capacitors during the portion of the voltage cycle, when the stored energy is returned to the source during another portion of the cycle. So it's merely slapping it back and forth between the source and the capacitor. There is no net energy loss. There is only storage. Okay, so let's take a look at the different types of power: instantaneous, true power, and reactive power. The product of little v, little I, this is our sub t values, gives us an instantaneous power. At points where v or I is 0, makes sense, power is equal to 0 because power is v times I. When both V and I are positive, the power is also positive. When either V or I is positive and the other is negative, the power is negative. Okay, when both V and I are negative, uh, power is negative. Whenever it's positive, it's positive. As you can see, the power follows a sinusoidal shaped curve, and we can see that here. Here's our sinusoidal power curve following the current and voltage curve. Negative values of the power indicate the energy is returning from the capacitor back to the source. Note that the power fluctuates at a frequency of twice that of the voltage and current as energy is alternately stored and returned to the source. Okay, so as we look at this, you can see for one cycle of voltage, we've got a complete, or a half cycle actually. For a half cycle of voltage, we've got one complete cycle of power. Okay, so it's double the voltage. The true power, P sub true, or PT, however you want to express it, ideally all of the energy stored by a capacitor during the positive portion of the power cycle is returned to the source during the negative portion. No net energy is lost due to conversion to heat in a capacitor, unlike that of a resistor. So the true power is zero. Actually, because of leakage and foil resistance, we know there's always a little bit of resistance in a capacitor and an inductor, we'll find out later, in a practical capacitor. A small percentage of total power is dissipated in the form of true power, okay, since it's purely a passive device. Reactive power then is the rate at which a capacitor stores or returns energy. The reactive power is a non-zero quantity because at any instant of time, the capacitor is actually taking energy from the source or returning energy to it. So this is following the sinusoid. Reactive power does not represent energy loss. The following formulas apply. So you can see it generally follows what we already know of Ohm's law and the power law. Okay, power is equal to the product of V and I. Power can also be V squared over R, or in this case X sub C. Power can be I squared X sub C. Notice that these equations are the same form as those for power in a resistor. The unit of reactive power is called VAR, VAR, because it's volt amp reactive. So let's determine the true power of and the reactive power in this simple circuit. Again, we've got an RMS value of the source at 2 kHz and tens, 100, so 100 microfarad capacitor. The true power is always zero for an ideal capacitor. The reactive power is determined by first finding the value of the reactance and then using our relationship. So X sub C, 1 over 2 pi F sub C, we calculate our reactance, 7.96 k ohms. Then we can plug it into the reactive power relationship. Since we have voltage, we can use V squared RMS divided by the reactance, X sub C. And when we do that, 2 volts squared divided by 7.96 k ohms gives us a volt, what did we call that? VAR, volt ampere reactive. Volt ampere reactive value of 503 micro, 10 to the minus third for our value. So we've looked at the reactance, how we use it in some simple series and parallel circuits, and how we calculate, in this case, true and reactive power.